Hello everyone, this is Mr. Kaviani, and by the end of this video, you should be able to calculate the acceleration of an object given the initial time, initial velocity of the object, final time, and final velocity of an object. Now, before we discuss this concept of acceleration, I want to draw your attention to two different forms of motion. Everything we've looked at in the course so far has focused on constant velocity. This is something traveling at a consistent speed. So, for example, the buggy car traveled a certain distance every single second, and it traveled that same distance every second. We didn't see the buggy car speed up or slow down during our lap. But as we all know, objects in real life do not always travel at a constant speed. Objects speed up and slow down all the time. For example, when you come to a red light, you probably, or you should hopefully, slow down. But when the light turns green, you speed up, right? Increasing your speed. And so we need a way to describe objects that travel at different speeds, objects that change their speed. And to do that, we'll talk about this idea of acceleration. Acceleration can simply be defined as a change in an object's velocity over time. Now, this can look a few different ways. Like the comic on the right shows, this could be an object that is speeding up or increasing its velocity. This could look like slowing down or decreasing its velocity. Or, because technically velocity is both magnitude and direction as a vector, changing the direction an object is traveling in is technically changing its velocity. And so our third option here would be changing direction, although this is something that we're going to deal with much less in this course. Now, I want to talk about the direction of acceleration because acceleration, much like velocity, is a vector. On the upper right here, I'll show my coordinate axis. I'm going to call left negative and right positive. So I want you to think about an object speeding up. That's if it's traveling in the positive direction, and then its acceleration is also positive. So I'll show that here as well, right? So if I show an arrow to represent the velocity vector, that would be like this. And acceleration would also be pointing in the positive direction. If I am accelerating in the same direction that I'm traveling, then I'm going to speed up. However, if that object is traveling in the same positive direction, but I'm slowing down, then what I'm actually doing is accelerating in the negative direction. Okay, now this sounds kind of weird. I want you to think about slowing down as actually speeding up in the opposite direction. Okay, so its velocity is becoming more and more in the other direction every second. And so for an object that is traveling to the right, eventually it starts to slow down, is what we say, and then it comes to a stop. And if it were to continue to accelerate, it would actually turn around and speed up in the other direction. And we'll talk more about that later. And then for an object changing direction, we won't worry so much about the direction of the vectors, but just know that the velocity direction will change. Kind of like if you're on a roller coaster and you travel in a loop, your direction's changing every second and you get acceleration, which we'll talk about later when we get to forces. For now, just understand that acceleration can simply be defined as a change in an object's velocity over time, and that there are a few different scenarios that can be considered acceleration. To calculate the acceleration of an object, we can use this formula triangle right here. And so what this tells you is to solve for any one of these three quantities, acceleration, change in velocity, the delta v, or time, you can rearrange for the others using the division and multiplication symbols in red. And I'll show you an example of that on the next slide. So just to define each of these terms, our time here on the right is our time, and that's going to be measured in seconds most often. This A on the left, as you might imagine, is our acceleration, and our acceleration is actually in the units of meters per second per second. Let me talk about that for a moment. What acceleration is, remember, is a change in my speed or velocity. Now, velocity is the measurement of how far I'm traveling in a certain amount of time, my meters per second. So what acceleration tells you is how my meters per second changes every second. Therefore, meters per second per second. How does my speed change every second? Now, we'll often just write that as meters per second squared, but I want you to think of it as meters per second every second, right? The rate of change of my velocity every second. Now, up here at the top, we have a fancy Greek letter. This is a delta. This means change in. So if you've seen this before, or if you haven't seen it already, a delta just means a change in something. Then a change in what? Well, v is velocity. So this means, right, this delta v is change in velocity. This tells me how my velocity is changing. And mathematically, we can write that as the final velocity, vf, minus the initial velocity, v, subscript I. So I show it with a little f and a little I. So that means if I take how fast I'm going at the end, right, vf, and subtract how fast I was going at the beginning, I can find the change in my overall velocity. Okay. So if you want to calculate delta v, right, you would just take acceleration and multiply it by the time, okay? If you want to solve for time, you would take the delta v here and divide by acceleration. And if you want to solve for the acceleration of an object, then you would take the change in its velocity and divide by the time. That's how the formula triangle works. You can just cover up the one that you're looking for, and then you have an equation for the other two. You can also just rearrange it algebraically if you're more comfortable doing that. We'll end today with a few examples. Let's say that you have a car accelerating from 0 meters per second to 60 meters per second in 3 seconds. What would the car's acceleration be? Well, I know that acceleration is defined as the change in velocity over time, which is my final velocity minus my initial velocity over time. And in this case, my final velocity is 60 meters per second, my initial velocity is 0, and the time was 3 seconds. So I will get 20 meters per second, or you can write meters per second squared. That's fine too. Okay, so in this case, we have a positive 20 meters per second, which means that our car is accelerating or speeding up. If you brake slowly, then that means your speed is going from 40 meters per second to 10 meters per second in 5 seconds, so we're slowing down. What would your acceleration be in this case? Well, that would be, again, the change in my velocity over time, my final minus my initial over time. And in this case, my final velocity is 10 meters per second, but I started at a speed of 40 meters per second. Then that happened in 5 seconds. So then my final acceleration would be 10 minus 40 is negative 30 over 5, which will give me negative 6 meters per second squared. And I want to point your attention, right? The negative here means slowing down. Because I was traveling in the positive direction, anytime we travel in the positive direction, a negative acceleration will tell us that we are actually slowing down. So that's how you can think about this. This is indicating slowing down. And then we have a car accelerating from rest at a constant rate of 10 meters per second. What is the car's velocity now after 5 seconds? So in this case, we're given the acceleration is 10 meters per second, and the time is 5 seconds, and we're asked to solve for essentially the final velocity of the car. We know that the initial velocity from rest means the initial velocity is 0. So if I set up my equation, A is delta V over T, then I know that delta V is my acceleration times my time, and that means that my final velocity, I'm not going to say minus initial here because initial 0 is equal to A times T. That means that my final velocity is going to be 10 times 5, and that's going to be 50 meters per second. And that makes sense, right? If we're increasing our speed by 10 meters per second every second, then after 5 seconds, I should have 10 plus 10 plus 10 plus 10 plus 10 meters per second. I'll show that in this chart right here. At time t equals 0, what is our speed? Well, it's 0, right? After 1 second, how fast are we going? Well, acceleration tells you that every second, my velocity will increase by 10 meters per second. So it's going to be 10. After 2 seconds, I'll be at 20. After 3 seconds, I'll be at 30. After 4 seconds, I'll be at 40. And then after, add a row here, 5 seconds, I'll be at 50. So each time 1 second passes, right, my velocity increases by 10 meters per second every second. That's acceleration. Okay, this concludes our video on acceleration. Please take a look at Canvas for problems to practice this concept.